You're building a feature, could be generating a PDF, running a complex AI workflow, or processing a bulk upload. You wire it up, and you wire it up the obvious way. The user clicks, the front end calls the back end, and the browser just waits. It spins, the user refreshes, and now the job runs twice. So this is request response trap. And today I'm going to show you how to get out of it. Hi, I'm Asan, and in this video, we are building the async push pattern, an architecture that offloads heavy work to the background and pushes the result directly to your browser the moment they're ready. No pulling, no spinners, and no timeout. So let's get into it. Look at this flow. The user clicks on an action, our front end sends a request to the backend API, and it starts doing the work. Now, it can be anything like PDF generation, a complex AI workflow, or file parsing. Whatever it is, the browser is just going to hold that connection open, waiting for that response. Now, three things that are going wrong here. One, if this takes more than 30 seconds, the browser is going to timeout. Two, if the user gets impatient and refreshes, that job is going to run again. You've now got duplicate processing, maybe duplicate charges, or duplicate data. And it can also result in corrupted data. Three, every one of these requests is a long running process that is running on your API server. So under load, this is going to kill you. The root problem is simple. You are using a request response mechanism for something that was never meant to be fit inside the single request. Now, here is the fix. The user clicks, but everything after that is different. So let me walk you through it step by step. In the first step, whenever the web page loads, the browser opens a WebSocket connection to our MQTT server and subscribe to a specific topic. Now, this is a persistent tunnel. It is silent, and the user has no idea that it is happening. But from this point on, the browser is continuously listening. Now, in the second step, the user clicks on an action, and our front end sends a request to the API, and then the API validates the request and then invokes a background job and immediately sends a response back to the front end. Now, that's the entire job of the API. It doesn't touch the heavy work, no blocking. The response is back under 100 milliseconds, and the server is already free. Now, in the third step, the job is now sitting inside a Redis in the case of BullMQ or in the MongoDB if you're using Agenda.js. Now, there are two things here. The first, the retries are automatic. Suppose if a worker crashes mid-job, then it can be invoked again according to your retry policy. The second is that you can run up to 500 jobs or any number of jobs concurrently without any of that pressure reaching your API server. So this layer is your safety net. Now, in the fourth step, the background worker picks up the job and starts processing it. Because this is running in an isolation, there is no timeout trace. The worker can take as much time as it wants to complete the job. And once the worker is done with the job, it can just picks up another. So in the fifth step, when the worker is done processing the job, it will publish a message to the MQTT along with the payload. Now, the payload can be anything. In the case of file parsing, it can be the data which it parsed from the file. In the case of complex AI workflow, it can be the result of running all of that workflow which the front end needs. So it is going to publish that to the MQTT server. In the sixth step, the MQTT server is going to push our message through Nginx via WebSocket to the browser, our client-side application. And our client-side application will be listening to the topic and will take appropriate actions according to the business logic. Now, it is possible that user has navigated away from that page, but it won't cause any problems because at that point, the front end will not be listening to the MQTT message. So the front end won't have to react based on the MQTT message because it is no longer listening. But if it is listening to the MQTT messages, then it can take appropriate actions according to the business logic of our front end. Now, the one thing that you have noticed in this diagram is that the MQTT messages are always pushed through Nginx when they are returned back to the browser. Now, this is not optional because our browsers do not understand TCP or MQTT protocol. They only understand WebSockets or HTTPS. So Nginx bridges that gap. And this is also where your SSL certificate lives. Now, if you're configuring an MQTT broker and you're configuring it via Nginx, it is possible that two things will silently break this if you do not add them into your configuration. The first are the upgrade headers. Without these headers, the Nginx never tells the MQTT broker that the WebSocket upgrade was requested, and the connection will die immediately on when it is opened. The second thing is timeout. So by default, if a connection sits idle for 60 seconds, the Nginx is going to cut it. But MQTT is idle most of the time. So it is necessary that you bump up this timeout limits so that users do not silently disconnect. Because if they do, they will not know what went wrong and why they are being disconnected. So this is async-push pattern, a lightweight API, an isolated worker, and a real-time push. Regardless of how long the background job takes to finish the task, your users will get real-time instant feedback on their client side.